Hello. Please hit like button and subscribe my channel. Also press bell icon for future video notifications. Thanks.
It's cool to be small. Scientists at the National Institute of Standards and Technology (NIST) have miniaturized the optical components required to cool atoms down to a few thousandths of a degree above absolute zero, the first step in employing them on microchips to drive a new generation of super-accurate atomic clock. The rapid, randomly moving atoms have only fleeting interactions with other particles, and their motion can make it difficult to measure transitions between atomic energy levels. When atoms slow to a crawl, about 0.1 meter per second, researchers can measure the particle's energy transitions and other quantum properties accurately enough to use as reference standards in a myriad of navigation and other devices. For more than 2 decades, scientists have cooled atoms by bombarding them with laser light, a feat for which NIST physicist Bill Phillips shared the 1997 Nobel Prize in Physics. Although laser light would ordinarily energize atoms, causing them to move faster, if the frequency and other properties of the light are chosen carefully, the opposite happens. Upon striking the atoms, the laser photons reduce the atom's momentum until they are moving slowly enough to be trapped by a magnetic field. But to prepare the laser light so that it has the properties to cool atoms typically requires an optical assembly as big as a dining room table. That's a problem because it limits the use of these ultracold atoms outside the laboratory, where they could become a key element of highly accurate navigation sensors, magnetometers and quantum simulations. Although other miniature cooling systems have been built, this is the first one that relies solely on flat, or planar, optics, which are easy to mass-produce. This is important as it demonstrates a pathway for making real devices and not just small versions of laboratory experiments, said McGee. The new optical system, while still about 10 times too big to fit on a microchip, is a key step toward employing ultracold atoms in a host of compact, chip-based navigation and quantum devices outside a laboratory. Researchers from the Joint Quantum Institute, a collaboration between NIST and the University of Maryland in College Park, along with scientists from the University of Maryland's Institute for Research in Electronics and Applied Physics, also contributed to the study. The apparatus, described online in the New Journal of Physics, consists of 3 optical elements. The enlarged beam then strikes a carefully engineered, ultra-thin film known as a metasurface that's studded with tiny pillars, about 600 nanometers in length and 100 nanometers wide. Moreover, by accomplishing that feat within a small region of space, the metasurface miniaturizes the cooling process. The NIST researchers designed the nanopillars so that the tiny structures modify the intensity, creating a beam that has a uniform brightness across its entire width. Please support my channel to grow by pressing subscribe button and the bell icon. We will notify you technological news. Thank you.